All right, so minimum spanning trees. So the minimum spanning tree for a weighted graph is a spanning tree with the smallest possible total weight. So we're kind of getting back into the smallest weights again. Now, examples of two spanning trees with weights are given. Is this one here basically the true minimum spanning tree or not? And so what we have to do is we're going to use the theorem on the next page to kind of decide that. And so remember, this was our original graph and it's weighted now, and before it wasn't weighted, but this is our original graph before we just had A, B, C, D, E, and F and stuff. And then what we did is we broke the BC part, and then we had this as our spanning tree. And this one we broke, I forget what it was, the DE part. And so that made that spanning tree. Well, then when we add these together, this one we found a spanning tree is 119. Here we find the spanning tree is 107. Basically, again, adding all the weighted sides together. Okay, so we deleted the 12 here and we deleted the 24 here. So those are the two possible spanning trees that we just came up with on our own. Now, again, could we come up with the different ones? Yeah, we could have came up maybe we could have deleted the 15 and had a thing like that. We could have deleted the 17 and so on. So it all depends on which bridge you break to make the circuit break. Okay, so that's kind of spanning trees. So now what we're going to use is Kruskal's theorem algorithm, and it's a procedure for finding the minimum spanning tree from a weighted graph. All right, so we're going to find the edge with the smallest weight in the graph first. Now, if there's more than one, pick one at random, and then we're going to mark it in red or whatever other way we're going to use the designation. Then we're going to find the next smallest edge on the graph. Now, if there's more than one, pick one at random. Again, doesn't matter. And we're going to mark it in red. And then we find the next smallest unmarked edge on the graph that does not create a circuit, because again, we don't want a circuit. So we have to create one that's not a circuit. And again, if there's more than one, pick one at random, then mark it in red. And then keep repeating that until all the vertices have been included. And the red edges are the desired minimum spanning tree, or the purple, or the green, or you erased ones, or however you want to do it. Okay, so it doesn't matter which way you want to do it. That's going to be kind of our method here. All right, so let's look at our example here that we had before. So if we're going to use Kruskal's algorithm, we're going to first find our smallest edge. Well, which one's the smallest? Well, it looks like 8 is going to be the smallest, right? So that's going to be our first one. Okay. And then what is the next smallest one? Well, it looks like, because it says next smallest edge on the graph is going to be what, 12, because that's the next smallest. So we'll say, okay, well, that's the next smallest. And then the next smallest after that, it's going to be 15. So that's going to be 3. The next smallest after that's going to be 17. So that's going to be 4. Now the next smallest will be 20. 5. Next smallest will be 24. But guess what? 24 makes a circuit. So we can't use 24. So then the only other one after that is 35. So that's going to be our next one. Now, if we add all those together, we already found out that that was 107. And so that means a couple of slides prior, it asked, is that the smallest one? Yes, that will be the smallest one based on Kruskal's algorithm here. Okay, again, finding the smallest one first and then working our way through all of those. All right, now let's do another one of these. This time, we have a lot more edges to have to decide with. All right, so first off, let's find the smallest one. So we have 24, 22, 28, 31, 35, 21. It looks like then to me, 12 is going to be the smallest. Okay. Then it looks like 14 is going to be the next. 15, 16, 21 probably is the next one after that. So that's going to be 3. And then where are we going to go from there? So 22, that looks like it would be the next one. So that would be 4. 23, well, I don't think we want to use 23 because if we go up here, come back down here, that makes a circuit, and we don't want that. So that one we're not going to use. Okay. And 24, if we come over here, guess what? That's going to make a circuit here because we'll go up here, go over here, so we can't use 24. 25, 26. Okay, 26. Well, if we do that one, we've come up here, we've come over here, and then that'll make a circuit here. So we don't want that one. What else do we have? 28. Well, if we make that, then so that's going to make a circuit there. So we can't use that one. 31 will be the next. that would make a circuit there, so we can't use that one. 35, that would make a circuit there, so we can't use that one either, doesn't look like. So it looks like we have a 12, a 14, a 21, and a 22. So 1, 2, 3, 4, 5. That gives us 4 edges. That should be good. So that's going to be 1, 2, 3, 4, 5, 6, and 2, 6, 9, 69. So our weighted total would be 69. And so our edges are going to look kind of weird. We're going to have A, the B, the C, the D, the E. So we'll have E, A, B, C, D. So we'll have that connection, we'll have that connection, we'll have that connection, we'll have that connection. So that would be what it looks like. And again, we can get from any of those vertices to any other vertice on there, and we're going to be okay. So that would be our minimum spanning tree for this example. And again, we just went and found all the minimum values until we didn't make a circuit. If we made a circuit, we had to cross it off, and then we ended up with our final value. All right, so hopefully that helps you with 14.4.